Perhaps these raps can help you alleviate the things that's got you tripping. You watch me demonstrate. First you ignore the nonsense and clear your conscience. Let your pen touch the paper, write verbs and consonants. As the words become a sentence, you start to feel indifferent. The stress is out your mind, you feel like the weight was...
Chapter 14.2 and simple harmonic motion. Simple harmonic motion occurs whenever the net restoring force of the system is directly proportional to the displacement x. And this is important, negatively proportional. An example of this was the mass spring system that we saw earlier. When we can jump directly to the exercise D in the textbook, which asks, which of the following represents a simple harmonic oscillator? So let's think about this one first. A. F equals minus 0.5 times x to the second power. This is not directly proportional because we have the exponent 2 here. So this is not a simple harmonic oscillator. What about B? F equals minus 2.3 times y. Well, this is exactly of this form, proportional constant being 2.3, so this is good. What about C? F equals 8.6 times x, x being the displacement. This is directly proportional, but we are missing the minus sign, so this is no good either. And the fourth D, F equals minus 4 theta, where theta is some angle. This could be the angle of a pendulum, for example, which we will see in the later videos. So this is directly proportional to the angular displacement, and we also have the negative sign here, so this is also good. So both B and D will exhibit simple harmonic motion when set into motion. The chapter 14.2 goes into great length in explaining you how do we get from a physical model like this that relates our displacement to the acting force. How do we get from here to say that what is a displacement at any given time? The derivation is done in the book, so I don't go into those details. It includes making an equation of motion out of this, which will be a second order differential equation, and then solving it. I will just recap the results. So the position at any given time of our mass in the mass spring system, for example, is the amplitude of the motion times cosine omega t plus some phase angle phi. This comes from solving the differential equation, and it also provides another important result, that the omega, which is also called the angular frequency, 2 pi f, is in fact k over m. So if we have our mass spring system, the mass hanging here, and this is a spring, or it could also be sideways, sliding on a surface. Whenever the k, or the stiffness of the spring is k, and the mass is m, the angular frequency of this motion will be square root of k over m. We can work this a little bit further by recognizing what is f. We know from before that F is 1 over t. So if we jump from here and continue another path, we have 2 pi f equals 1 over t, where t is being the period of the motion. We can solve for the period. T would be 2 pi over omega, and we know that omega is k over m. So this becomes 2 pi m over k. Let's make that one better. M over k. So this is an interesting result. The period of the motion depends only on mass and the stiffness of the spring, but not on the amplitude of the motion. So if we have the spring going between these two positions all the way here, then changing directions and goes here, the period of this motion would be the same as if this mass would swing all the way here and then all the way there. So whatever the amplitude of this motion, this is called the amplitude, let's call it A2, this would be A1. It has no effect on the period of the motion. So you would imagine these two masses moving in unison, except that the other one ventures further to the left and further to the right. But they would be synchronized, if you will. No analysis of motion is complete if you don't also include velocity and acceleration. So velocity is always the time derivative of displacement. So if we take time derivative of this one, we get minus omega amplitude A sine omega t plus phi. And this can be written in the form of V max times the sine of omega t plus phi. Because whenever we have something in front of the sine, that is the amplitude of the signal. So in our case, this would be the V max. The maximum velocity of the mass at any given time will be omega A, and omega can be written as k over m, so we can write A times k over m. Then acceleration is in turn the time derivative of velocity, so we will get minus omega squared times A, go back to cosine omega t plus phi equals minus A max in the same fashion, pick up the amplitude from here, and cosine omega t plus phi. And in this case, the maximum acceleration is from here, omega squared times A, which can be written as A times, and the square will take care of the radical, ak over m. As we can see, for simple harmonic motion, the displacement, velocity, and amplitude, they are all sinusoidal. So whenever we have simple harmonic motion, it means sinusoidal motion, whether it's cosine, sine, cosine. They're all examples of sinusoidal signals or sinusoidal functions. The most important stuff to take home from this is definitely the period of the motion. It is only defined by the physical parameters of the system, the mass m and the spring constant of the spring, or the stiffness of the spring k. Also important to remember the basic form of displacement in simple harmonic motion. It is sinusoidal motion, and we have the amplitude A here denoting the maximum displacement from the equilibrium. Also, these formulas might come handy at times if you want to know what is the maximum velocity that the mass is going to achieve at any given point during the motion, or if you want to find quickly the maximum acceleration of the mass. As usual, we will have a couple of exercises from the book. Before we get started, let's put the most important results, what I just showed. So the angular frequency of the motion, of simple harmonic motion, is square root of k over m. And also we have the period of the motion, 2 pi over omega, which will be 2 pi m over k. We should also write out that the actual frequency of the motion, which means how quickly does it vibrate back and forth, is embedded in this angular frequency. So angular frequency omega equals 2 pi times the real frequency of the motion. Now, the exercise E asks, by how much should the mass on end of a spring be changed to halve the frequency of its oscillations? So we have a mass at the end of a spring, and we want to halve the frequency. So to solve this problem, we had to find an expression for frequency first. So we'll start from here. The frequency f equals square root of k over m divided by 2 pi. So if we want to halve the frequency 2 over frequency 1 needs to be 1/2. What is f2? f2 is square root of k over m2 divided by 2 pi, and that thing divided by f1. f1 is k over m1 divided by 2 pi. So 2 pi's cancel, so do the k's. So we are only, okay, so this is equal to half. So we are only left with, within a square root expression, we have m1 that jumps all the way to the up, m1 over m2. So this needs to be half. So we raise the whole thing to the second power. m1 over m2 equals 1 over 4, from which we can solve. m2 will be 4 times m1. So what do we have to do to the mass on the end of a spring? M2 is 4 times M1, so it has to be quadruple. In exercise F, we are supposed to find the frequency of the motion that is being described by this expression, displacement x. To solve that, let's write out the general form of simple harmonic motion, the other important result from the previous slide. So it's always of the form amplitude A times cosine of omega t plus the phase angle phi. The frequency lives in the omega, the angular frequency, but it's not the same as we see from here. We want to solve for the f, so omega being 2 pi f, we get f equals omega over 2 pi. Okay, where do we find omega? Let's have a look at this expression again. So we have 0.8 meters. That is the amplitude of the motion. Here we have the phase angle phi, which is minus 0.25 radians. And our omega is here, 3.14, which is same as pi, about. So we have pi over 2 pi, which is 1/2, 0.5 hertz. That would be option C.
Country chillin' in my LA Express on every street corner. The importance of having fun. Empty bottles, spill tobacco. Don't nobody carry guns. We keep our minds on fun and let the drums do the banging. On any given day, like Mr. Cooper, yo, we hanging under the blue sky.